All right. Hello, everyone. Thank you for joining us today for this online workshop. This is hosted by the Natursea-PV project. That's a European project we'll hear very soon. And the title of our meeting today is Ultra High Performance Concrete Innovation, Practice and Sustainability. I also want to thank our speakers for today's meeting, that are Mrs. Edurne Erkizia, Mr. Peter Butelar, Dr. Ben Tarup, Dr. Wu Yenle, Professor Bernard Middendorf, and Dr. Esteban Camacho, that also part of, together with Edurne Erkizia, who is our project coordinator. Also, Esteban Camacho is part of the Natursea-PV project. So without further ado, I'd leave the stage to Edurne Erkizia.
Okay, thank you, Claudio. Just upload my presentation. Can you see my presentation?
Yes.
Okay, so I would like to welcome everybody to this industrial workshop. And as Claudio said, it has been organized within the Natursea-PV project. And before we start with the subject, which is the ultra high performance concrete, I'll just have a short. I will give a short description of the project. So, okay. This project has been funded in the context of the European Green Deal. Well, Europe has the ambition to become the first climate neutral continent by 2050, with the objective that the green transition must benefit citizens and businesses. Renewable energies play a key role in that green transition. However, most renewable energies require large areas for gigabyte scale electricity generation. So placing them on the water seems a smart solution. But offshore floating photovoltaics is still in an early research and development stage, and Natursea-PV's project's objective is to bring these offshore floating photovoltaics closer to reality. So the strategic objective of Natursea-PV is to improve the overall lifetime, reliability, and maintainability of marine substructures for offshore floating photovoltaics, to reduce degradation and failure rates, and thus investment risk and levelized cost of electricity. So the requirements from the European Commission for the projects were to develop the substructure design with circular materials to withstand wind speeds higher than 25 meters per second, strong currents higher than 1.2 meters per second, large waves higher than 40 meters, and also withstand corrosion and biofouling for the substructures. Test and validate new prototype components and materials, research materials properties and behavior, and develop improved predictive computational modeling tools. In Natursea-PV, we proposed a substructure design based in nature. We proposed first in the water lily, the design in the water lily, and it has been evolved, this design, to withstand the harsh conditions of the sea. So we have studied different substructure designs and models. Then for the substructure material, we have based it on ultra high performance concrete. This ultra high performance concrete, it's because its increased durability. It has increased durability on harsh environments. Life cycle assessment shows that it's more sustainable than standard concrete. Ultra high performance concrete allows for reduction of material use and increases lifespan. And the multi-cracking and autogenous self-healing characteristics of pre-stressed ultra high performance concrete makes it resilient to even the harshest environment. So as I said, we based our development in ultra high performance concrete, in particular in the Formex, developed by Prefor and RDC. And in the project, we wanted to develop it, however, using it low clinker cements and also geopolymers. Besides this, we also are developing bio-based coatings, starting from bio-based monomers, which come from biomass instead of petroleum. And the idea of these coatings is to reduce fouling and reduce harsh ion attack. We are also developing new predictive computational toolkit for durability, durability prediction and for maintenance planning. So we are doing microstructural model of the matrix, developing modeling of surface treatments, developing multipath transport models, and also mechanical models. And we want to combine all these models to develop the predictive computational toolkit. We also want to test our solution at lab scale, but also in realistic conditions. So in fact, we have already tested the superstructure prototype at lab scale in the basin test that Marine has in its headquarters. Recently, we have also placed the specimens made of the developed eco-ultra high performance concrete and biocoatings on the offshore harsh lab platform that Tecnalia has off the coast of Biscay. And they're going to be there around 6-8 months. Then we're going to take them back to the lab and analyze them for fouling or chloride ingress. And later in the project, we are also producing beams with the developed materials, the eco-ultra high performance concrete, to see if they can be used for industrial production. And we'll put them, these beams will be placed in the ocean. Besides the development of the materials and the substructure design, we also want to assess the environmental and socioeconomic impacts that deploying these floating offshore photovoltaics may have in the sea, in society, and also in stakeholders that live off the sea. And we also want to enhance social perception by means of workshops, organizations, courses, webinars, networking with clusters, and etc. In the consortium, we are 11 partners from Portugal, Spain, France, Italy, Germany, Netherlands, and Ireland. And let me now just explain briefly some of the developments in eco-ultra high performance concrete that we are doing in the project. First, we set up the requirements for this eco-ultra high performance concrete. It has to be self-compacting, open time maintained for 20 minutes. The 24-hour compressive strength should be higher than 65 megapascals. At 28 days, compressive strength should be higher than 130 megapascals. We want to reduce the carbon footprint more than 30% and include more than 35% recycled or second life materials, for example, second life fibers. Usually, ultra high performance concrete are prepared with OPCs, especially CEM1. We're using large amounts of CEM1. In this occasion, we want to use, as I said before, lower clinker cements. These cements we've used have been provided by Holcim. Also, we've used superplastic acid developed by Fosroc and Bauchemy to obtain the mixes. And for recycling, substituting, we have decided to substitute steel fibers for second life fibers from flexo fibers. Just a brief summary, we have been able to obtain mixes with the three cements with the right mini slump flow, right open time, the 24-hour compressive strength achieved the requirements. At 20-day compressive strength, it's slightly lower than 130 megapascals in the mixes we've obtained, but very close. And if we plot the embodied CO2 of the developed eco-ultra high performance concrete versus obtained compressive strength and compare it to the standard ultra high performance concrete, in this case Formex, produced by Prefor RDC, The Eco-Formex, for example, which is also have been developed by Prefor RTC, maintains the mechanical properties but with lower embodied CO2. The other mixes developed in the project also have high compressive strength, a bit lower, slightly lower, but with low embodied CO2. And if we compare it to literature data, we see that our mixes follow the trend. And I would like to mention that these mixes have been developed at lab scale. So we believe that going to an industrial scale could improve further the mechanical properties. And this was just a brief description. And with this, I finish my talk, and we can get into the ultra high performance concrete subject. Thank you for your attention.
Thank you very much, Edurne. So before going on with the speakers, there were our partner and friend Esteban that wanted to say something and to personally thank all the other speakers. Esteban, are you with us? Yes.
Yes, I am here. Well, I am Esteban, one of the part of one of the partners of the project Natursea, and I wanted simply personally to say thank you to the speakers. When we decided to organize this event, we had a wish list of who we wanted to speak, and all of these persons that were in the top said yes. So I am very thankful, and I think today we are going to learn a lot. So Claudio, we can start already, or we can continue. Thank you.
All right, thank you very much. So our first speaker is Mr. Peter Buitelar from Peter Buitelar Consultancy. And Mr. Buitelar has been working with UHPC for 40 years, so he's going to teach us very much, probably. Thank you. We can see your screen.
Yes. Big thanks to Natursea and Esteban for the invitation to share some of my knowledge and experience with UHPC during 40 years with colleagues from all over the world. I strongly believe that practical experience contributes to future knowledge, and that knowledge should be shared and transferred to future generations. Two important developments and inventions are made by Hans Hendrik Bagge. The development of world's first UHPC in 1978 by using ultrafine particles well dispersed with a high doses of superplasticizer between cement particles. In 1986, Hans Hendrik Bagge developed compact reinforced composite and the technologies behind this development. Both inventions are a major part of my career, and my contributions to the use of UHPC are based on those two inventions and the future developments. What is durability? According to the engineering choice, durability is defined as the ability of a material to remain serviceable in the surrounding environment during the useful life without damage or unexpected maintenance, when faced with challenges of normal operation over the design life. Durability should be understood as the ability of the constructive system and its materials not to exhibit significant deteriorations that imply loss of functionality for which they were designed. In this sense, more durable constructions reduce maintenance and repair costs and reduce the environmental impact that would be caused by the exploitation of new raw materials and the generation of construction waste in case of the need for demolition. The durability of a building or structure must meet at least the design working life, and during this period, the necessary maintenance procedures that should be specified for the system must be met. What is durability for UHPC? Durability UHPC is a performance, and the required durability depends on the application of the specific UHPC. How more durable the UHPC how long is the design life and the actual service life of the structure or component. There is no one does it all UHPC, and not all the UHPCs have the same properties of performance and thus the same durability. Durability UHPC is not per se depending on the compressor strength, but direct or indirect on the density and the properties of the microstructure of the hardened matrix. The density and property of the microstructure of the hardened matrix depends on the use and the type of ultrafine particles and the packing model to fill the spaces between the cement or other particles. We call this the binder. Durability can be tailored by using other types of cement, cement replacement materials, or no cement as the main component of the UHPC binder. Durability UHPC can be tailored for specific applications by combining reinforcement fibers and aggregates with the specific UHPC binder. The first UHPC has been used since its development in 1978 for many, often unique, performance-based applications. Each field of application or business area has its own durability demands, and therefore testing durability of individual UHPC mixes and components or structures was required during the first decades, or continuously like in the security industry or for protective structures. Each business and application have its own requirements regarding the durability of the specific UHPC. A summary of the tens of different performance-based applications will be impossible today. Some performance-based applications are or were very successful, but also many future developments were initiated. Many performance-based applications were not typical concrete applications, but replacing other materials like, for example, steel, asphalt, or ceramics. The durability of a safe, vault, ATM safe, or strong room is simply based on obtaining accessibility for burglars to their content and the time and tools necessary, so-called resistant units, to access the content by creating an opening of certain dimensions. The total amount of resistant units is directly related to the insured value of the content. How high the resistant units are, how high the classification and value storage covered by the insurance. Wall thicknesses of 40 to more than 250 mm are used. To create a high durability performance of the security object, often innovative solutions are adopted to make it as difficult and time-consuming as possible for burglars to access the secured object within a certain time. Most often, the accredited test institutes have very specialized burglars to test a security object, and knowing and observing the methods using make it possible for the supplier to anticipate and make innovative solutions to complicate and delay these specialized burglars and the real potential burglars. Requirements, classification, and test methods are described in detail for safes, ATM safes, strong rooms, walls, and strong room doors, and part of the structure, like anchoring and base, in the many standards worldwide. For confidential reasons, test methods and innovative solutions are not shown in the requirements, classification, and test methods. However, all books and documents from producers in the security industry are giving interesting insights about innovative use of various materials. Abrasion erosion resistance is durability performance needed in dams, locks, and sluices. To investigate the very serious abrasion erosion in the Stilling Basin of the Kinsua Dam in the United States, with holes up until 1 meter deep, and recently repaired some years before, several products, including HPC and UHPC, were tested and compared with the original concrete. The specified unreinforced 1,540 cubic special design DSB concrete by my former colleague Eigil Sørensen, with a thickness of 30 centimeters and with a compressor strength of 90 MPa, was placed in sections. I would have designed another solution by using the best tested UHPC as a 50 millimeter thin bonded overlay on the DSB concrete, like what we do in the Netherlands in locks and sluices. Ultra-thin bonded UHPC toppings have been used since 1985 to repair concrete structures like locks and sluices in the Netherlands. The UHPC has been applied underwater by divers and where floor layers when a temporary closure was possible. An annual 7 to 10 centimeter abrasion resistance, abrasion erosion by sand, larger materials and bicycles and other large objects has been stopped. Underwater inspection after 10 years showed a removed cement skin on top of the very hard aggregates. The underwater abrasion resistance test, ASTM-C 1138, evaluates the durability of concrete surfaces when exposed to hydraulic forces and suspended abrasive materials, as commonly encountered in hydraulic structures. The test quantifies the abrasion resistance by measuring the mass loss of concrete specimen subjected to a rotating propeller in water containing abrasive particles, steel balls, which are steel balls with different diameters. The same ASTM test was done in the laboratory from Edelka in Porto das, Venezuela, in the early 1990s, to investigate the suggested solution to protect the existing steel-lined inlet to the turbines with an abrasion-resistant UHPC concrete and avoid further damage to the turbines. The test resulted in before unseen low figures. Problem was that the steel balls eroded when they touched the very hard calcined bauxite aggregates of the UHPC. The entrance to the inlet was only possible by entering a small manhole, and Edelka decided to anchor and weld small steel plates on the existing steel lining, with as a consequence that the extreme fast-flowing water containing abrasive particles removed the anchored and welded plates very fast and destroyed the turbines. Caroline Priest from the Danish Corrosion Center investigated durability of the new, in 1980, UHPC materials in the early 1980s with regard to abrasion erosion and corrosion. Abrasion erosion or cavitation erosion is a large problem in the industry when abrasive materials like silica sand, coal, cement, glass, etc. are hydraulically or pneumatically transported in systems with high velocity in huge amounts. No test method can simulate the very complex phenomenon of the actual wear in a system. Particle size, hardness, dimensions, angle of impact, temperature and speed to all contribute to the abrasion of materials. Several standards and own developed tests are used to test UHPC for wear protection, because the first commercial supplier of UHPC was not only 100% owned by a large cement producer, but also part of a very large industrial group supplying to the cement industry. This made real-life testing on sites possible, often with spectacular outcome and a service life extension from sometimes days in normal steel to months or even several years. For example, wear linings, cyclones, ventilators and transport linings, sometimes in very large diameters, can be lined with UHPC. In some cases, the UHPC is exposed to very high temperatures, up to 1200 degrees, and or aggressive products. UHPC can, like a traditional concrete, be designed and used for several application methods. Prefabricated elements, manual application, poured between an inner and outer liner and sprayed. Often UHPC could replace other materials in machine parts like cast iron in the scope feeder for the cement industry. We also see that UHPC designed for optimum protection against wear doesn't show any relationship between compressive strength and abrasion and erosion resistance. The type, quality and dimensions of the special aggregates embedded in the strong grip of the UHPC binder are responsible for the wear resistance and impact resistance. For industrial floors, pavements, concrete repair and bridges, other properties and durability are required. The combination of extremely hard aggregates and steel fibers, durable fixated in dense UHPC, are resulting in extreme high wear and impact resistance. Industrial floors and pavements are used, especially in the heavy industry and the food processing industry, and they need to fulfill a huge amount of durability performances, from hygienic and easy to clean to impact resistance and flatness. To the unique properties of the ultra-thin hybrid reinforced UHPC overlays, they can be placed on almost every subbase, even when they are cracked or polluted. For rehabilitation of often polluted floors in large workshops and because of strict requirements from the authorities, all penetration in the UHPC was needed to be tested in the early 1990s, and we see a maximum penetration depth of only 0.5 millimeter. Durability is also resistance against fatigue. For the replacement of a 150 mm thick wooden deck on a Basco bridge in a highway with prefabricated ultra-thin hybrid reinforced UHPC with a cover of only 10 to 50 mm on the reinforcement, several additional tests were required by the Ministry of Infrastructure and Water Management. Fatigue test of 2 panels in the laboratory resulted in amazement by the engineers present. If you want to see concrete flutter, look to this. Amazing how flexible a plate with these dimensions can be. You see the plate clearly bulge under the load. The weakest factor in this panels is the reinforcement. How stronger the reinforcement, how stronger the plate will be. The reduction of fatigue-related problems of orthotropic steel decks by applying a thin bonded hybrid reinforced UHPC, early done on container ships and a dry dock, has been very successful. UHPC application, which is now used worldwide as a rehabilitation method. Fatigue tests on cracked and uncracked orthotropic steel decks with the thin bonded hybrid reinforced UHPC have been executed and shown impressive service life extension up to 75 years. Also, the stress reduction by applying a thin bonded hybrid reinforced UHPC on the orthotropic steel decks showed an impressive service life extension up to 125 years. The predictions were not only proven in the laboratory, but also on actual products where the bridges were monitored. Shrinkage and curing can significantly influence the durability of UHPC, and especially when UHPC is used in an aggressive environment like offshore and on bridge decks. Evaporation of mixing water in UHPC with already a very low water binder ratio will result in unwanted shrinkage, cracks and delamination. The amount of evaporation of UHPC placed on large surfaces and the effect on the durability is often underestimated. Cellevolt investigated in the early 1980s the frost resistance and ice formation at extremely low temperatures in UHPC and concluded that there is no ice formation taking place at ordinary freezing temperatures. We are talking about -50, even when the paste had undergone drying wetting cycles and is tested in saturated state. Thus, it is suggested that the microsilicon containing DSP concrete could be made resistant to frost action without air entraining agent. Many other Scandinavian researchers, including my former colleague Eigil Sørensen, came to the same conclusion. We are using this when we are applying UHPC industrial floors in blast freezing in the food industry in special tunnels, where in less than 5 hours the temperature is going down to -40 degrees Celsius and going up again to 20 degrees Celsius plus. Research for the strengthening of orthotropic steel decks in 2002 confirmed that the 28 cycles from -20 to +20 degrees Celsius resulted in an average mass loss of 4 grams per square meter, compared to 100 times more mass loss of the reference 60 MPa concrete. Also, the adhesion of the tin-bonded hybrid reinforced UHPC on the orthotropic steel decks was tested using the same 28 cycles. No delamination occurred. Research for the strengthening of the orthotropic steel decks in 2002 confirmed that 2 years exposure to chlorides only resulted in chlorides in the top slice of the cylinder. We are talking about less than 3 millimeter. Unfortunately, the test had to stop due to the lack of enough samples. Spillage of acids on industrial floors, industrial pavements and structures, but also in transport systems which have a wear lining is common. Early tests with different concentrations of acids and application in chemical plants showed a good chemical resistance compared to high quality concrete. UHPC tests with chemicals in various concentrations and at different temperatures show a good acid resistance compared to high quality concrete. Interesting is that UHPC made with aluminate cement often showed even a better resistance. The use of UHPC for prefabricated units for the storage of nuclear waste has been investigated in the early 1980s. For use as corrosion protection of offshore platforms, UHPC has been investigated at the Danish Corrosion Center in 1986. This included forced cracking of the UHPC layer. Lake Maracaibo, an oil-rich basin located in the northwestern Venezuela, is particularly interesting location from a corrosion control standpoint to its unique environmental conditions. The lake water is very corrosive. There probably are other areas in the world that are more corrosive, but there is no other area of comparable corrosivity with as many industrial facilities built in the lake. An external layer of UHPC has proven to be an excellent solution, which is also strengthening the platforms. All studies in the 1980s and 1990s confirmed an excellent protection of steel and steel reinforcement. Corrosion of fibers and/or reinforcement in UHPC has been investigated by Aalborg Portland researchers and test institutes since the early 1980s as part of the durability performance. While first corrosion tests were done on unloaded specimens, later research as part of a Eureka and a Bright Journal project were focused on highly loaded specimens to simulate the behavior of real-life structures and to initiate exposed to wet drying cycles to salt water and dry air. Also, UHPC shotcrete shows in 10 mm layers a very low chloride diffusion coefficient. First performance-based applications of UHPC are executed since 1978. In practical applications where durability was often the most important factor. In the security industry and protective structures, wear protection in the industry and civil engineering, offshore and civil engineering. UHPC has a proven durability performance under extreme conditions. UHPC is a concrete with an ultra-high performance, and UHPC can replace other construction materials and can be used in new composites and new composite structures. Durability, slenderness, and efficient use of resources by developing new UHPC mixes is making UHPC future-proof and a material with a huge potential. Durability UHPC is a performance, and durability requirements are depending on the application of the specific UHPC. Since UHPC is more used, sometimes even overused, and more suppliers of UHPC are active in the worldwide market, it is important to document this performance. Before a UHPC is accepted for a specific application in a specific field of application, not only a proof of concept, but also a material approval request is required to ensure that the specific UHPC meets the standard and specifications. The classification UHPC by the producer and the compressive strength only is not a proof of durability performance for a specific application. Based on the specific application, standards and tests must be applicable and repeatable in both laboratory and, if necessary, on-site. Too much testing on UHPC is done just for the testing purpose and without any practical value for real-life applications. It is therefore extremely important to determine the required durability requirements of the UHPC for a specific application or a specific area of application, and to record these in a schedule of requirements for the material approval request to fulfill by the supplier producer of the UHP FSC. Make information regarding the durability of UHPC international accessible in a UHPC knowledge center and include extensive information from the first decade since the 1980s. Standards, specifications and tests for UHPC should be the same to be able to compare durability UHPC from the many suppliers worldwide. The Secretary General of the UHPC Branch Association of China Concrete and Cement-Based Products Association, Dr. Yun Zhao, wrote on the memento of the e-lecture on UHPC in 2020 the following recommendation: gaining knowledge from the past for new developments and better creations. Thus we should learn from the past to perform better today and tomorrow. Thank you very much for your attention and excuses for my long presentation.
Oh, don't worry, Peter. It was perfect. Thank you very much. We still do not have any questions, so we can proceed with the next speaker. And the next one in line is Dr. Bernd Arup. Are you with us? Yes.
Yes, I am.
So he is a civil engineer with more than 35 years of experience in working with UHPC, and he will talk us about this 35 years with UHPC. How are things now compared to before, and what are documentation and sustainability requirements? Is it right?
Yes.
Thank you very much. You can go on.
Yes, I'll I'll try to start this. I think I started something live instead. Does this look okay, or do I have to do something else?
Yes, it looks okay for us. Try
Okay.
to
Yes.
To change the slide just to be sure.
Yes.
Yes, it works perfectly. Thank you very much.
Okay, thank you. Yes, the title of my presentation is 35 years with UHPC and how things have changed over the years with regard to documentation and sustainability. I started working with UHPC in 1987, so I can't quite match Peter Beutelaar with regard to experience with this type of material. In my presentation, I'll just make a short introduction to Hycon, our company, and the type of UHPC that we use. I'll talk a little bit about early applications and what we do now. And then I'll move on to some of the documentation requirements and especially sustainability requirements. So it'll be about 50-50 between discussion of the UHPC and the documentation requirements. This is the company I work at, Hycon, a small precast UHPC producer that started in 2001 and is based in north of Denmark. Actually, in 2001, it was a much smaller scale when it started up, but this factory was built in 2006, and it looks the same today with a few small extensions. This is the stockyard. We produce everything according to a contract, so very few standard products. And based on that, you could say that we needed to have very little stock, but in practice, we know projects get delayed or we have to produce ahead of time because installation is faster than the production. So it means we need a small storage facility anyway. We produce no conventional concrete, only UHPC, and the type we use is the CRC that Peter Beutelaar already presented. It was developed at Aalborg Portland by Hans-Henrik Bagge in 1986, and then we've used it since the start in 2001. It's very similar to a lot of the types of UHPC that you see today. very high strength matrix with steel fibers, and in our case we also use conventional reinforcement together with this type of matrix. So compressive strength 150 to 400 megapascal, depending on whether we use heat curing or special aggregates. In our production, average strength is about 170 megapascal for the things that we produce. Bending strength depends on the rebars. Young's modulus, again, depending on the type of aggregate we use, but we're typically around 45 gigapascals with our normal mix. We have to have a good fire resistance, as most of our products are used in buildings. And when we use slender elements and we want to include rebars, we have to have very good durability, because we normally have a cover to the reinforcement of 10 to 15 millimeters. The first applications of specifically of the CRC were made around 92, but the applications that Peter Beutelaar shows was very similar to CRC. Over the years, more than 120,000 tons of this type of UHPC has been produced by Hycon. We always use steel fibers with our mixes to ensure that we have strain hardening, to have good crack control. And the graph shown is from a standard test EN 14651 with some relatively large notched bars. But we want to make sure that we get multi-cracking performance, so we have a very ductile behavior for the concrete. This shows some of the first precast architectural applications where, as Peter has mentioned, some of the applications earlier were in bridges and things like this. But if we want to have a production that goes on every day with a lot of UHPC being produced, we needed to find other types of elements. And what we found was that the architects were very interested in having very slender products, and products where they could make large balconies or very large staircases and make them very slender, so that you didn't have a lot of load on the building itself. So this, from an early stage, this was what we looked at, and it has continued over the years. So also today, balconies are by far the largest product by volume that we have. And these are some examples of recent projects. We produce a lot of our products are sold in Denmark, but also in Northern Europe. These are examples from Sweden, Norway, and Finland, and we also sell products in Holland and in England. We've sold some elements in Gibraltar, in Bangkok, and we recently sent some balconies to Bondi Beach in Australia to be put up, and they look very nice on the beach. Other types of elements that we produce are staircases, where again we can utilize the high strength of the UHPC in torsion and for the large spans, and to make the very slender, almost floating types of elements. This is an aspect that really appeals to the architects. One thing that we were interested in from the start as engineers was bridges, but it was very difficult for us to get started with UHPC bridges. It wasn't until we had the first applications in Holland and set up a small sales company in Holland that they started asking about bridges, whether we produced those, because they had a lot of canals in Holland, so it needed a lot of bridges. And of course, bridges are not so difficult, so different from staircases or balconies. So we produced a few bridges in Holland, and have also produced bridges now in Denmark and in other countries. Facade elements is a very big application around the world for UHPC, but we have only produced a few projects, one in the Middle East, the rest of them in Northern Europe. But it's because a lot of the facade applications are in Middle East, in China, in United States, and that's markets where we don't have we don't know so much about the markets and the players on these markets. So this is not something that we've done a lot of. I mentioned the documentation. This is what we had early on. Our documentation when we started out with the first applications for CRC was based on international research projects that we'd carried out and a lot of documentation that we'd achieved. For especially at the time when CRC was developed in 1986, it was very different from the types of concrete that you could see in the market. So we knew we had to find out what about durability, what about shear resistance, what about fire resistance, all these kinds of things, because we knew we'd have to document any applications that we started out with. This shows some of the reports and some of the full-scale tests that were carried out. So this was the system we used for the first projects. If we did a project in Copenhagen, for instance, the building authorities would ask questions about fire resistance, for instance, and I'd show up with a stack of reports and go through all the questions that they had. And luckily, Denmark is a relatively small country. So next project we'd have in Aalborg, they know already that we had a project approved in Copenhagen. So we didn't need to find all the same reports, perhaps a few others. But it worked this way for a long time. And as the references piled up, it became easier and easier to do this. When we started doing projects in other countries, we could not just show the references in Denmark. For instance, in Holland, when we did the first project, we had to have a third-party reference report made. In this case, it was Professor Valraven from Delft who did it to certify that our calculations and our properties were okay for the types of applications we were looking at. And we also did a full-scale test for the first project we did in Holland. But as we were getting into 2012, 2015, the requirements for documentation changed a little bit. We had been asked earlier about the CE marking that we have in Europe for building products. And we could say confidently that we couldn't make the CE marking because you have to do it based on a harmonized standard. And there were no harmonized standards for UHPC. But especially Finland, they keep requesting this CE marking. Otherwise, they would not be able to put up any of the products. So we started to look further into, was there a way that we could achieve this CE marking for our products? And we found out that we could make an EAD, European Assessment Document, that could be made for a specific product. In this case, it was made for balconies in UHPC. And after this, we can make an ETA, a European Technical Assessment. And this takes the same role as a very specific standard, and it's approved by the European Commission. And then we can CE mark. And after that, it was much easier to have, especially the international applications. When we have the CE marking, you make a declaration of performance that's very similar to the identity cards that are used in some of the other guidelines. We knew by 2017 there were already guidelines around the world in Canada, US, the SIA in Switzerland, and the national Eurocodes for UHPC that have been put up in France. Germany has already worked with guidelines for a long time for UHPC, but we couldn't really use these things or these guidelines directly for the applications that we had. So we've been going the route of this EAD, and at the moment we're preparing EADs for other products, like columns, beams, staircases, and things like this to make the approval process easier for us. We're well aware that work has started up on Eurocodes for UHPC, and we'll be having the 5th meeting of this group in France in the autumn. But we also know that work like this will be going very slowly. So it will be perhaps 5-6 years, if we're lucky, before we have Eurocodes on UHPC. And at that time, it will, of course, be much easier. This just shows you the EAD and the ETA and the CE marking for this special application. Another issue that have been coming up with regard to documentation is sustainability. We first met it actually in projects in Holland and in Norway about 15 years ago. And at that time, it was not a big thing in Denmark. The CO2 the carbon footprint of your materials. But over the years, it's been a very, very big thing. And we're aware that the building industry in Denmark is responsible for 30% of the CO2 impact and 35% of waste. So the building industry has to do something very specifically to reduce the load on the environment. We've had a certification in Denmark called DGNB since 2012. It's a German system that mainly looks on 3 criteria: economic, environmental, and socio-cultural criteria, and to evaluate buildings or neighborhoods to make sure that they can get an approval before they are put up. And we've done that on a lot of buildings. But starting in January 2023, a more strict limit was started up in Denmark, where it was stated that a building, if you want to put it up, it has to have a carbon footprint below 12 kilos of CO2 per square meter per year. And that's everything. That's use, that's putting up the building, that's everything that goes into it. And if you can't meet this requirement, you don't get a building permit. We had expected this limit to be reduced over the years, so it would be 10.5 kilos in 2025 and so on. But very quickly after this was put in motion, it was decided that if we want to meet the Paris goals of temperature rises, then we had to reduce it to 7.5 kilos actually from July this year to speed things up. And I know some projects will really have a problem meeting this limit. But of course, based on this, we knew that we had to look at the sustainability of our products. We had done an EPD, the Environmental Product Declaration, back in 2018 already. So we knew that if we look at this per cubic meter of material, then we don't look so good. We had about 1,050 kilos of CO2 per cubic meter for cradle to gate, the A1 to A3, similar to our Spanish friends. But what's interesting is that if you look per functional unit, for instance, square meter of balcony, then because we have very slender elements, then the load is not very high, and we're about 30 to 50% better than conventional concrete if we compare, and about 25 to 30% better than steel if we look on a balcony. So we have a large advantage of this, being able to make very slender elements. Also uses less material, so less raw natural resources, less load on the buildings, etc. So these EPDs have to be renewed every 5 years. So even though we've done one for balconies, and we had to renew it in 2023. We're looking, and we're doing it also for staircases and other elements. But this is one thing. We know that we're doing okay compared to concrete and steel, but we also know that we have to improve. And one way of improving is to reduce the cement content, as you also found out or know in the Natursea project. We've done some projects where we introduced larger aggregates in a UHPC. Normally, what we used in the factory until about 2 years ago was a mortar with a maximum aggregate size of 4 to 5 millimeters. But in putting in larger aggregates up to 8 millimeters, we could reduce the mortar content and the cement content. And this was done for the bottom is some segments for a windmill turbine tower, and the bottom is for Catharina Bridge in Holland, a small bridge. So this is one way where we can reduce cement content. Another way is to introduce fillers to replace cement, or we can use just some of the new cements that are put on the market. Traditionally, we've used a CEM1 as basis for UHPC, but in February this year, we changed to a CEM2. So this means combining the large aggregates and the CEM2, we reduce cement content by about 30%. So, and cement is responsible for about 62% of the EPD carbon footprint. So it's really something that has a large significance. And these are some examples of the new types of staircases, standard staircases that we're doing with this mix. We call it I3B, and this is because the concrete that we used prior to this was called I2, and the B is because we use a little bit of bauxite sand to have a stiffer and stronger mix, which means we can reduce the thickness of staircases and balconies even more, and have less carbon footprint that way. One new thing that we're looking into that will be for the future is to have reuse of elements. In a lot of cases, I know in London, for instance, it's very difficult to get approval to tear down a building and put up a new one. You have to go to a lot of lengths to reuse as much as you can from the old building. This is something that we've seen in the past. The bottom left picture is from a project in 2000 where a building in Aarhus was pulled down, and they wanted to reuse some of the old beams, but with the new building system, the beams were a little too short, so we used the CRC joint cast dry mortar version of our UHPC to extend the beams a little bit so that they could fit the new system and be reused. This is something that we're looking into with the balconies and our staircases. A lot of our balconies are put on after the building is actually put up to make it easier to for the logistics of it, and to make sure that we don't make cold bridges for the building. And this means that it will be very easy when the building has to be torn down. It will be easy to take off the balconies and perhaps reuse them, because balconies are expected to have a service life of 150 to 200 years, whereas the building will probably not last quite as long. But as the first balconies were put up in 97, it'll still be a long time before we can actually do this. But this is something that we've already started to look into, to have the circular economy. So we're doing some things, not quite as much perhaps as in the Natursea project, but we are also aware that because we've had to establish a lot of documentation, we have to be very careful each step we take. It's very easy to replace 50% of the cement with a calcium filler or slag or fly ash or something like this, but we have to be very sure that we don't reduce durability of our mix, and we don't introduce other problems with regard to fire resistance or anything like this. So it's important that we take very small steps, because UHPC has been developing for a long time. And while carbon impact is very, very important, we have to make sure that we don't compromise with regard to ductility and durability. Thank you for your attention.
Thank you very much, Bent. We have actually a lot of questions for you. So let's try to answer at least a couple of them. So one question is from Herman Weyer. Dear Ben, very interesting application of your material. How is certification done? Is it covered by a Danish code or guideline?
No, it's not. It's covered by. It's based on the ETA and the EAD that we developed, and this is in the European EOTA system, which means that every European country has some agency that has approved this ETA. In Germany, it's DIBT. In Sweden, it's RISE, for instance. And when we have this ETA, then we get the CE marking based on normal certification, like a normal precast company would, where they come out and see, do we fulfill all the normal requirements for concrete according to EN 206 and the special requirements that are stated in the ETA. And then based on this, we have a certification. But we are already aware that when we look at projects in other countries, we may get other requirements. For instance, we've been looking at a project in Germany where they've asked us to adhere to the SIA code. And of course, we'll do this.
All right. So another question by Budvin Pisker. Since silica fume availability is rather unreliable, is ultrafine high purity calcium carbonate not an interesting alternative?
We've looked at a lot of alternatives. Microsilica is very, very good. But there are some issues now also with the CSRD requirements in Europe, where we have to be more aware of where the materials are produced. And the white silica fume that we get is produced in either India or China. So it's a long distance to get it from. So we've looked at other types of material also. The very fine calcium carbonate, and typically we don't get quite as good performance as we do with the microsilica, so we're very slow to change.
Thank you. So there's another interesting question from Danilo Di Giacinto. Interesting applications, Bent. Thanks for sharing. As the elements you showed are more demanding in terms of bending and shear than compression, have you considered using short high performance hooked steel fibers with slightly larger aggregate instead of 13 millimeters micro steel fibers and standard aggregate for UHPC?
Yes, we have a little bit of because bond is so very, very good in UHPC, we have a little bit of an issue. If we use hooked end fibers, they tend to break. And what we want to have the very ductile performance is we want to have pull out of the fibers. And we can get this if we have sometimes 12.5 millimeter length, sometimes 20 millimeter length. And with 20 millimeter length, we actually get a very good performance. So we don't get an added performance if we use the hooked steel fibers. I should also mention that in order to have an easy approval, we don't normally include the performance of the fibers in our calculations. It's typically very easy to achieve the performance we want with just the rebars, so it's quite enough. For a lot of applications like staircases and balconies, it's really stiffness that determines the design. But with the new NXL coming up to the Eurocode, we've started to look at introducing the fiber performance also in our calculations, because before we had this NXL approved, it was a little bit more difficult to get approval in Denmark for this.
All right, just another question, and then we will move on because we have to. So this is from Prasad Savekari. When you try to use 8mm aggregates to reduce carbon content, is it also possible to use higher diameter and longer fibers?
Yes, we prefer not to use higher but it is possible. Some years ago, we used a fiber that was 0.4 millimeter in diameter, and it worked quite well. The reason we reduced it is because of price. From 2009, we only used stainless steel fibers because it's not because of durability or strength, but because of the aesthetic aspect of our architectural elements. And this means that the steel fibers are the most expensive part of the mix. So we've done a lot to reduce steel fiber content and still get the same performance. And one of the ways of doing this is to increase the aspect ratio up to a certain limit until you get problems with mixing. So first thing we did was to reduce the diameter of the fibers, and second thing we've done is to increase the length a little bit. But as you know, it decreases. It decreases workability. So that's why we have two lengths of fibers. So if it's a very complicated casting, we use a little bit more of the 12.5 millimeter fibers. But if it's a relatively simple casting, we use 20 millimeter long fibers, and then we can reduce and get the same properties of the mix.
Thank you. Thank you very much. So we are going to move on, but Bent, there's another question, and you can find the question in the above toolbar in the Q&A section on the menu. So if you want, you can directly answer to Javier Alanis. I think it's pronounced like this.
Yes,
so you
yes,
can,
I know.
you can directly comment on his question. We're going on, and the next in schedule is Dr. Vu Yen Lei from Dura Technology. Dr. Vu Yen Lei is the founder and CTO of Dura Technology, and he's going to talk us about the concrete environmental performance potential of UHPC bridge. So, all right. We can see your presentation.
Right.
Yes.
Thank you very
now
much.
It's full screen. Thank you very much.
Can you see my presentation? Is it in the full screen now?
Yes.
Okay. All right. Okay. Thank you. Okay. My name is Dr. Wu. Today, I'm going to talk about the environmental performance and durability of ultra high performance concrete bridges. Okay. Here is a statistic which I collect from China. Back in year 2023, the annual consumption of UHPC in China alone is about 146,000 meter cube. So, which is around, in terms of value, which is around 150 million USD, and it has a growth of almost 80% compared to year 2022. And the key applications for the UHPC in China, which you can see here, is 39% goes to the bridges, and about 70% to municipal and hydraulic engineering. But 1/4 goes to wind turbine tower, and with the balance, the remaining goes to the building construction, and only about 1% goes to repair and strengthening sectors. And for India, India also is one of the country now has been increasingly using these UHPC technologies. I have got this from some source, which is the KPMG, where they predicted the minimum demand of UHPC by year 2032, which the UHPC value will be around 380 million USD. And we are expected by year 2032, there will be around 23 UHPC manufacturing plant. Okay. So there are many applications of UHPC, which Peter have shown just now. But today, my focus is only talking about the UHPC bridges. Okay. Our basically Dura company was formed in year 2006, and we have been in business almost about 19 years. So we have how to say, we have put our foot into different part of the world, such as China, India especially. Okay, so by now we have constructed about 400 numbers of UHPC bridges in Malaysia, China, and India. And only Malaysia alone, the latest number which I have is we have so far done about 280 numbers of UHPC bridge from different, from small scale up to quite a large span. Yeah. And the UHPC we produce generally using only one type of fiber. And our UHPC have about 1.5% by volume of steel fiber, and the size is 0.2 millimeters in diameter and 20 millimeters in length. And the fiber content is about 119 kg per meter cube. Okay. Okay. Here is the the experimental data, the experimental curve of the UHPC which we use, and this is the direct tension test based on the Ashto method. So with 1.5% of steel fiber, the UHPC will have a first crack around 11 MPa, and you can see that then after the crack, it will continue to continue to deform, and the peak is also around 11 MPa. So in our design of our bridges, normally we will use a post-crack characteristic tensile strength of around 8 MPa. And with the factors come in, which is the material factors of 1.3 and the fiber global orientation factor of 1.25. So basically the design tensile strength which we use is about 4.8 MPa only. Okay. So what is the advantage of using UHPC bridge system? First of all, with such a high strength material, our structures will be thinner and lighter. And of course, with this material, it has an extraordinary durability and also have a high strength to weight ratio. And definitely UHPC will give you a much longer service life. And it's also aesthetically pleasing using a pre-stressed concept. And with this material, it's increased the resistance to corrosion and abrasions. And we believe this system is almost maintenance free, and it definitely have a much better sustainability indexes, which also in our projects, in our decades of experience, we realize that these UHPC bridges actually have an immediate time and cost saving. And with all this benefit coming, we strongly believe that the UHPC bridge system is a life cycle cost saving technologies. Here is my first case study, which is called the Sungai Langat Bridge, where you can see here is the crossing, this crossing which is crossing the river. They have a simple span of 105 meters. Okay, and this bridge has also received two very prestigious awards from United States, which is the PCI award and the American Concrete Institute Excellent Award. So the UHPC we use for this project basically is to cast a precast U beam, which is also they are assembled at the site using a post-tension method. One U beam is around 105 meters long and they weigh around 400 tons. Okay, and one full beam, they have around about 14 segments. Each segment is around 6.5 to 8 meter in length. So they're all manufactured in the factory environments and then transport to the site and then reassemble near the site and do the post tensioning and grouting before launching onto the piers. Here's a video which I would like to share with you. How do we launch these 9 girders? Okay. This project basically demonstrate with such a high strength material, it changed the way we construct bridge. For such a span 105 meter, conventionally, people will either go for a steel composite bridge or a balance can deliver construction method. But with UHPC, we actually have made a breakthrough and try something different from the conventional way. And here's an example of the comparison of the steel composite bridge versus the UHPC composite bridge. The steel girder in this project, if I'm using the equivalent amount of steel to take the same loading, the amount of steel I needed is about 3,000 ton, and it will cost around 6 million euro at that time. And our UHPC girders, which is nine girders, is cost less than 3 million euro. So you can see that immediately they are more than 50% of cost saving. Then I also use this concept called the CEPP, which is a concrete environmental performance potential, which it just been published in the FIB model code, the latest FIB model code, where the CEPP is defined as the FCK times the service life divided by the EIC. EIC stands for environmental impact calculations. Okay, so based on this simple equation, we can make a comparison of this UHPC system versus the steel composite bridge system. Okay, so here is some of the inventory data. Okay, it shows that with different grade of different strength, different grade concrete, they would have a different embodied carbon and embodied energy. So the embodied carbon we are using for the UHPC case would have only consist of 1.5% of steel fiber. In this case, will be 1158 kg CO2 per meter cube. Okay, so with this inventory data, we can do a comparison. So the EIC basically is equal to the embodied energy or embodied carbon multiplied by the material quantity. So in this case, the deck is actually exactly the same. I mean, the RC concrete deck is exactly the same. It's only the girder is different. So with this material quantity multiplied with the inventory data, we will have yielded the total EE, EC, and the global warming potential in tonnage. So here is the comparison. So what this diagram show is the UHPC superstructure is about 18% heavier compared to the steel composite bridge. But the embodied energy is about 65% lower, and the embodied carbon is about 58% lower, and the 100 years global warming potential is about 59% lower. So here, immediately, we have seen that the UHPC is a better system compared to steel composite bridge, first of all, where I've shown just now, the cost also immediately have a 50% saving. And also the long-term performance, definitely the UHPC will be perform better because it do not easily corrode, especially near to a corrosive environment when you compare the steel. Because steel idea, there's still required maintenance, routine maintenance over the years. Okay, here is another example, case 2, and this is a girders. I would say this is should be currently the world longest UHPC girders constructed for a railway bridge, and the span is 80 meter. Okay, and you can see from here is, okay, we are comparing. This is basically is a railway bridge. The conventional design, which is which there normally is a 40-meter span, but there's one special span which is 80 meter using the UHPC. The initial structure actually is a 40 meter with one pier in the middle, but due to some reason during the construction, the pier in the middle are not able to be constructed. So during the construction, they make an alternative. So the chance to use a UHPC girders. So here, I would like to also to do another calculation, which if we are comparing this UHPC with a normal box, normal strength concrete box girder, what it show is the UHPC composite bridge have a immediate 22% saving in terms of width. This also including the substructure and the foundations. Okay, and embodied energy is about 10% lower, and embodied carbon and global warming potential is also around 11 to 12% lower compared to the conventional design. Okay, and this is how the conventional or the conforming design looks like, basically using the grade 40/50 pre-stressed concrete box girder and versus the UHPC systems. Okay. Okay. In terms of durability, we have used this fixed law to predict the durability. So these bridges are actually constructed at a location 1.4 kilometer from the coastal area. So the structure are generally in the exposure condition of XS1. So based on some of the empirical formulas, we got the airborne salt at this location have a salt of about 1.128 kg per meter cube. So we plug into the fixed law, and then what it shows is generally the structures would have achieved more than 120 years of service life. So if we plug into the the CEPP, what it shows is the UHPC composite bridge is about 30% better in terms of the sustainable performance compared to the normal strength concrete box girder bridge. If assume that if this bridge are constructed at just right near to the coastal area, which is in a region which is D equal to 1 meter, the airborne salt will definitely higher compared to the just now example. So in this case, the airborne salt we are using 6.42 kg per meter cube. So then we continue to use the calculation. What it shows is the box girder would have a service life reduced from 120 years down to around 37 years. Okay, so then we put into the CEPP formulas. What it says is the UHPC composite bridge would perform 5 times better than the normal conventional concrete box girder in this extreme environment. So my conclusion is UHPC compared to steel bridge is 20% heavier, but at least 50 to 65% less embodied energy and embodied carbon. UHPC compared to normal concrete bridge in normal exposure is around 10 to 20% lighter and 10% to 20% less embodied energy and embodied carbon. In normal exposure conditions, UHPC structures is around 30% better sustainable performance than normal concrete structures. But in a highly corrosive exposure conditions, UHPC structures is around 500% better sustainable performance than a normal concrete structures. Thank you.
Thank you very much, Dr. Wu. We have a question for you from Christian D'Amico. The question is, UHPC bridges can be very thin. What is your experience with dynamic behavior, especially with cable-stayed UHPC footbridges?
Okay. See, so far, I mean, from our years of experience and with the amount of the numbers of the bridges we have constructed, I put it in a very simple layman term is, if steel composite structure or steel bridge can be used, then these UHPC structures generally they are about 20 to 30% heavier compared to the steel structures, So if steel structures conventionally it can be used, definitely this one also not much an issue because the mass of inertia is still higher than steel. So so far there's no complaint or whatsoever regarding to the vibration or the dynamic response of these structures, even though for footbridges or even though for traffic bridges, then that is our experience.
Thank you very much. So we can proceed. Now the stage goes to Professor Bernhard Middendorf from the Faculty of Civil and Environmental Engineering of University of Kassel. Professor Middendorf also has a huge experience and also he's also one of the organizers of the International Conference on Ultra High Performance Concrete and High Performance Materials. So he will tell us more about sustainable and eco-friendly UHPC. Professor, the stage is yours.
Yeah, thanks a lot for the kind introduction and hello to everybody. Yeah, a lot of things we already have heard, but I like to focus on sustainable and eco-friendly UHPC. And I have divided it in two parts, in the material science aspects and construction aspects. Construction aspects, I got a lot of slides from my colleague, Professor Fehling, who is the head of the concrete construction department at University Kassel. So I'm sure that not everybody knows where is Kassel. Kassel is quite simple, is in the middle of Germany. It is the heart of Germany. We have unique combination of urbanity, cultural landscape, and I can tell you it is nice to visit, and you have to do it once lately in 28 when we have the next Hypermat. There's our university. We have 25,000 students. And in the department, in my department of building materials and construction chemistry, we have a lot of instruments to prepare UHPC and measure the properties of it. And we go then to the Department of Structural Concrete to Professor Fehling, who can do real tests. So, and here you see one of the buildings in Kassel, that is the Gärtnerplatz. You will see another thing. So, coming to the German definition of UHPC, that is a progress report from the German Committee of Structural Concrete. It's an ultra high performance concrete. It's a very dense, fine or coarse grained concrete. Fine or coarse grains, that means everything, with a compressive strength, to 150 to 230 megapascal. It is a high-tech built material for construction of high, sustainable, sophisticated, lightweight, and cost-effective structures. That's the official definition. And it is only possible because of the invention of superplasticizer, what you see here. In former times, we have only cement, aggregate, and water, and then we could reduce the water-binder ratio dramatically because by using superplasticizers. And what we also do is we use optimized packing density, and then we can produce UHPC, and we have heard it in the lectures before. Here you see the first bridge in Germany. It's a Gärtnerplatz bridge, Garden Place Bridge. It was constructed in 2007, and it was designed by my colleague from the structural concrete department, Professor Fehling. And this was made of steel and UHPC. And here, this is only, you see, hopefully the mouse is only 8.5 centimeters thick. And this construction is only possible with UHPC. Then we can use UHPC for other things as bridges. Here you see the stadium, and here Musem, the museum from the architect Ricciotti, and so on. So, but we have heard it already what we can do with UHPC, also balconies in Denmark and the Netherlands. So, but when we look to the UHPC footprint, okay, a production of 1 ton of cement is approximately, that means 0.75 tons of CO2. And a traditional UHPC contains up to 800 kilograms cement per cubic meter, probably 750 or less, but it's some typical values. So, but what we need is to reduce the CO2 footprint. We need novel concepts and designs, and we need a paradigm shift. I got this picture from my colleague Hundes. I think he's also in the audience. A paradigm shift is a change in the basic assumptions within the ruling theory of science that was from the philosopher Thomas Kuhn. And what is meant is shown here. That is Dirk Fosbury, and he was the first one who make high jump backwards, and that is a paradigm shift, so that you see what I'm meaning with what we have to do. So that means to improving sustainability, we have 2 paths to improve it. So we can increase the performance, or we can saving resources and reducing CO2 emissions. So that means what I like to show is novel applications first. So that means we are here in the performance field. Optimization of the UHPC properties and the use of new technique to enhance the durability and to improve novel application. One can be additive manufacturing. We can make lightweight concrete, hybrid elements, or use innovative materials. Here, I have to accelerate, otherwise I will not run out of time. Additive manufacturing. So that means you can produce thinner and lighter with dedicated structures, and you get a better performance with less material. So, and what we do also in Kassel, we have the typical UHPC with a very dense microstructure, high strength, high load capacity, high durability, and everything. We use this idea and use the matrix to prepare a lightweight concrete. So that means we call it UHPLC, ultra high performance lightweight concrete. So that means we have a strength approximately in an area about 100 megapascal, but we can then combine it with UHPC, with original UHPC. So you see it here. We have hybrid elements for multifunctionality. So that means we combine the UHPC, you see it here on the right. We combine UHPC shells, traditional, and put in a very dense, not a very light UHPC, but with a high compressive strength in the area about 100. Or what you can do it fresh in fresh. That means first you prepare it horizontal, the UHPC, and then put the light UHPC on it, and then you have a multifunctional element. And we are now trying to build small houses like Lego houses using these elements. That means we have reduction of cost and energy in the construction process. The next, I think that is a really interesting innovation, but it is far away from application. We can use shape memory alloys. You know shape memory alloys probably from braces, or hopefully not, but from you use it also for stands, or here for a wheel of a lunar vehicle, or you use it in aircrafts. And very famous, the older of us know him, Uri Geller, who used the shape memory alloy spoon in the late 80s in the movie and got very popular. But what is a shape memory alloy? A shape memory alloy remembers his shape. So that means, and then we can use this for using in UHPC. So what you see here, hopefully you see it. Yes, you see it. I have a curled fiber and put it in hot water. And what we have done first, we have the untreated shape memory alloy fiber. Then we curl it. And when it gets a thermal impulse, it gets in his original state. So that means we have heard from the presentations before that the fiber content of a UHPC is approximately 1.5 volume percent. Okay, you can do it till 2.5 volume percent, but then it is not workable anymore. But with this trick, with the shape memory alloys fiber, which we curl, we can, and here you see it here, you have the fresh UHPC, then you get a thermal impulse. The fiber goes in, I show you again, goes in this original state back, and then you can add up to 6 volume percent of fibers into a UHPC, and this allows you to make the system you like to produce and to use in a building, you can make it much thinner and lighter. And here you see yield stress and plastic viscosity, so that means untreated and cold fiber. So that means the rheology is much better when you use this in the same amount instead of traditional fibers. Also, you can use shape memory alloys for pre-stressing applications. It's very interesting. Here you see it is from Reefer in Switzerland. They put it under a bridge deck and then heat it up. It reduces length, and so you have a kind of pre-stressing. What you also can do, and we have done it also in Kassel for research, you can pre-stress with shape memory alloys bars, put it in, you don't have to prepare it, and then give an impulse in it, and then you have a pre-stressed application. And here you see shape memory alloys in comparison to carbon lemon and non-reinforced references. Good. So here, what you see, that is a nice video, I think. You see it also and now it goes back in its original structure. So that means you can use the shape memory alloys in UHPC, but also for the preservation and in the use for buildings and infrastructure, especially when you have in an earthquake region, you can use it for retrofitting when structures are damaged and or loads are increased due to change of use, and they allow very smart characteristics. Okay, then we have a project, and the head of this project is Professor Kunders from the Technical University of Darmstadt, and there we have a huge project from the German Research Foundation. It's called, the short form is Net Zero. So that means it is SPP 262436. You can Google this project or just go to Eddie Kunders' webpage at TU Darmstadt. And here you see the CO2 emission of today's concrete. So at first you use for the production a lot of, you have to produce a lot of CO2, then it carbonates a little bit. That's today's concrete. And our idea is to go up to to a CO2 neutral point. And there we have 3 blocks. That means carbon neutral binders, renewable aggregates, and concrete carbon sink. So, and I have one part together with Eddie Kunders. So that means when you look to a traditional building material like cement, you use the cement, you have calcium sulfates in the Portland cement plus water plus your aggregate. And then over the time, you have chemical reactions, you get the CSH phases and calcium hydroxide, and the result is you get your concrete block. When we now supplement the Portland cement, that means we reduce this part and add some reactive wastes. I don't like the word waste, so recycled materials, active materials over the times, then we have the same reaction products, but we also have some silicates in the waste ashes. We get more, or at least it's a kind of substitution amount. We get the same amount of calcium silicate hydrate in the cement, but we have lower costs and more sustainable concrete. So when we look what is able on the market, on the right side, you see the SCM's availability. We have silica fume. That was a question of one in the first talk. We have waste glass, vegetable ashes. We have natural porcelain a lot. Slag, fly ash, we have to discuss. It is used and is available, but the question is how long. We have Portland cement, we can produce it, but we have a lot of fillers and we have calcined clay. So that means natural porzolans and all others, we have enough, and then we can produce these cements with this. And then we have to use these cements for preparing UHPC. So it was in the talk from Bernd Arup that he said that he used once a SEM2 with Portland limestone cement instead of a pure SEM1. So I think in the future we have to work on it, that we have to use different kind of more eco-friendly cements. And then we also have our alternative SCMs, that means volcanic ash, I told you, and we have also agricultural ashes from street wheat sugar and what you see here. And the point is that is the ash content of the plant. Look here, rice husk. It means you have 20%, when you burn it, you have 20% of ash, and there in the ash you have 93% of silicate, which will react, and then we have to identify what kind of material we can use as SCM in cements, which we can use for UHPC. And here you see pictures from Cuba where they have the sugar canes, and that is the sugar cane ash, and from a time they had 30 million tons of it. And very famous at the moment, it's a hot topic, we have limestone calcinated clay cement, short LC3. So that means here, LC3, you have the calcined clay. Here you have the strengths of some different concretes. That is the normal OPC. And then here you have concretes with different amounts of clays, and you see that when you use a Calonit, or we are working also on it, that you sometimes get a higher strength than with the normal OPC. What I have done once is, sorry, I used not LC3 in UHPC, because LC3 means you have limestone, calcinated clay, and some others. So what I have done is I used a normal UHPC mix is Z1, 77% cement, 23% silica fume, and then I substituted LC2. That means only limestone and calcinated clay, 10%, 20, 30, 40, 50. And then I looked to the compressive strengths after 7 and 28 days. So the first one was without 150, and after 28 days, 205 megapascal strengths. And when I substitute 10, 20, 30, 40, 50, so you see that is only 50% Portland cement in it. All the others are I show you again. All the others is limestone and calcined clay mix up to 50%. Then we have here, after 28 days, a strength of 137. And what I have also done, I not used a German cement, I use different kind of cements. Also, I use some Brazilian cement just to get ideas what we can do. And here we have used a Brazilian cement, and here 115 megapascal after 7 days, 160 after 28, and with 50% we have 110. And now we have to think if 110 or 140 is not, or if it is enough to use it as a UHPC. Then what we also do is we work also on absolutely cement-free systems. We work with geopolymers and alkali activated materials, and we produce also UHPCs. Wobei C is not right, but we produce UHPC material by using geopolymers and RMs. And now we started a project with the Deutsche Bahn, that's our German railroad system, to use these materials for some prototypes. Okay, here in New Zealand it was already done, and you see that they use 33 prefabricated panels here make of this material, and we like to use it for some prototypes, but the aim is more to test it, but we can reduce the CO2 footprint. Also, what we can do is, it's also together a project with the Technical University of Darmstadt with Eddie Kunders. We combine the SCM part with bio-based aggregates. So that means here we have a reference without biochar. We have 100 megapascal, and then we use different kind of biochars. I can talk 1 hour about this topic, but I just give an idea. Biochars from agriculture waste. Of course, it reduces the strength, but we can use it as then with the idea of the dense matrix of UHPC as a normal concrete, and we come close to net zero. That are the ways what we can do in the material science. Coming now to the construction, and we saw some examples from Dr. Fu, but here what we like to do is reducing the ecological footprint. We have to change the design of our structures, but we have to keep in mind safety, long life, low cost, sustainability, construction process, maintenance, recycling, all these things we have to keep in mind. So you know all these things, the relevant properties to describe the ecological footprint. Here you have the non-residential buildings and so on, and that is the emission part, 40% approximately. But we have to reduce CO2 emission, we have to reduce material, and so on. So, and then you have also your life cycle phases of building structures, I'm sure you already know this. But now I like to go here in the phase A1 to A3 in the production. That means what we have to do is we have to reducing material and water consumption by utilizing of high performance materials with better durability, enabling reduction of maintenance frequency during lifetime, optimization of structures on the level of structural members and whole structure. And I like to give you 3 examples from my colleague Feeling, is here mentioned. We have a long span roof girder, a structural slab, and a pedestrian and cycle bridge. But we are only looking here in the phase A1 to A3. So here it's an alternative design of a roof girder as a single span girder with a span of 31.2 meters for an industrial hall in Central Europe. It's not so big like the Chinese example of the bridges, but here normally you have a pre-tensioned girder, weight of concrete C50-60, volume 7.4 cubic meter. You can do the same with UHPC. When you change the design, you reduce the volume, and what you see is you have a reduction of CO2 emissions. That is the girder with 3,000 or say 4,000 to less than 3,000. That means you have a reduction of volume and you have a reduction of CO2 emission. And now you have to combine this, what we also can do from the material part. So that means we can reduce the cement in the UHPC, make it more eco-friendly with SCMs or less clinker-intensive cements, then we can increase these values. Another example is an alternative design of a structural slab, a single span slab with a span of 6 meters for standard buildings. That is a standard slab, and that is made of UHPC. You see here 1.7 cubic meter per meter, and here only 0.3. Reduction again in volume, 83%, reduction of CO2 emission, approximately 70%. And coming back to the pedestrian Gärtnerplatz bridge in Fulda, normally you have to do it like here, pre-stressed concrete bridge made of C3545 with a box cross section, and now made of UHPC. And here we have also a high reduction of primary energy consumption and a high reduction of CO2. Okay, another example, what you can also do, and Peter, we wrote a special edition, I'll show you later on. We can reduce, or we can reduce an old bridge by using a thin load-bearing overlay of UHPC. So that means UHPC layer within situ concrete of bridges replaces traditional waterproofing for superstructure, and is the UHPC layer is part of load-bearing structure. So that means you have the old bridge, and now you put a thin load-bearing overlay of UHPC over it. If you like to read more, there is a special edition. So Peter is one of the authors. It is a Beton- and Stahlbetonbau. That means concrete and steel concrete construction, and it is bridge repair and reinforcement with fiber reinforced UHPC. And here you can see the whole knowledge we have more or less in Europe for the bridge repair by using fiber reinforced UHPC. Coming back to the Gärtnerplatzbrücke, it was finished in 2007. And oops, yeah, you see it here. It's a steel construction. And then here we have a 8.5 centimeter thin UHPC layer on it. We do a monitoring since that time, and it's still in a really perfect condition. So also, that is an example from Bruwiller from Lausanne and my colleague Fehling. So what they have done, normally you have a bridge deck like here. Here's a railroad track. Here you have the bridge deck, which is very thick because it's made of concrete. And now you can here, using prefabricated rib plates made of fiber reinforced UHPC, it looks like this. And in reality, it is here. You see it. You see a train going over it. And here you have a sketch, and here you have the finished building. So that means with UHPC, you can save a lot of material, and by saving a lot of material, you can save a lot of CO2 and make it more sustainable. And here, one of the last examples, that is a rehabilitation of a historic steel bridge with UHPC, and you see here is UHPC, and you can use that, and that is the same what Dr. Fu told us, but he was comparing steel bridges with UHPC bridges. I have compared traditional concrete bridges with UHPC bridges or parts, and that is how it looks like. and then I like to finish, or I have to finish. In former times, we have these requirements and values, all what you see here, load-bearing capacities. That's what we all talk about when we talk about concrete. But nowadays, we are also focused in these aspects. And my colleagues and I, we think we have to go to new values in constructions. That means neutrality, circularity, frugality, and so on, what you see here. So that means the traditional things, what we have discussed at the time where the CO2 footprint was not so important, but nowadays we have to go like here. And now I come back to the University of Kassel. Please make a note that in March 28, we have the 7th International Symposium of Ultra-High Performance Concrete and High Performance Building Materials for Sustainable Construction at our university in Kassel, what we have every 4 years. And hopefully, I see at the moment we have 85 persons here in the audience. Hopefully, I see all of you then in Kassel, and thanks for your attention. And I hope I could give you some ideas what we can do with this sophisticated material. Thanks a lot.
Thank you very much, Professor Middendorf. We have 2 interesting questions for you. The first is from Andres Ayuela, and he asks, what kind of shape memory alloys are being used? Normal one with titanium nickel would be very expensive?
Yes, okay. We tried to get a big project with this, but it was unfortunately rejected. NITIs, nickel titanium, you pay approximately 15,000 euros per kilogram. That is not good for a bridge construction by using UHPC, but nowadays on the market, a lot of people are working on iron-based shape memory alloys. And these iron-based shape memory alloys, they have magnesium, aluminium, silicium, so it's a very complex alloy, but it have more or less the same properties than the nickel titanium alloys. The nickel titanium alloys are not so durable in the high alkali medium of a concrete, but we have worked with, and also I showed you the retrofitting from the Reef company in Switzerland. They use iron-based shape memory alloys. Of course, they are at the moment expensive, but think about the carbon nanotubes. When they started coming on the market, you paid 1,000 euros per gram. And nowadays you pay €1 for 1,000 gram. It depends how it is used in industry. And I'm sure that the shape memory alloys will get much cheaper in the near future, but it depends how many people like to use it. And it will not be used for traditional UHPC structure. It will be used for very dedicated structures. Probably, and Arup can make 1 centimeter thin balconies in Denmark with using 6% of these shape memory alloys.
Thank you very much. The second question is by Budvin Pisker. Alkali-activated geopolymer cements are in a revival mode, especially since they have much lower CO2 emissions and they have high chemical and fire resistance. How can these binders be integrated in UHPC?
No, they are not integrated in UHPC. That means I will not mix OPC, UHPC with a geopolymer. What we do is, and I showed you the regulations from the German, so that means what is the definition of a UHPC? A definition of UHPC is that there is cement in it. That's the definition of a concrete. But we can prepare a geopolymer, say it's not a concrete per definition, but say geopolymer concretes or AAMs with compressive strength up to 150, 160, so that we can use these AAM concretes in the same like the UHPC concretes with cement. We don't mix UHPC with, we don't mix it. So it's a different thing, but it's also very dense, durable, and has a definitely lower CO2 footprint.
Thank you very much. So we can proceed with the last speaker of
Thanks
today.
a lot, everybody.
Thank you very much. We can proceed with the last speaker of this workshop. Then is Dr. Esteban Camacho, and as you know, he is already part of Natursea-PV project. And he also a civil engineer with more than 15 years of experience in the design and production of precast UHPC elements. And he will talk us about UHPC quality control, latest innovations and distinctive approaches. Esteban, I think you're ready. So the stage is yours.
Good afternoon. Thank you very much. Do you hear me, Claudio?
Yes, and now we can also see you.
Okay, perfect. Well, we are going to speak about quality control on UHPC, and particularly about how we control UHPC in our factory to make it reasonable and efficient. The first I'd like to clarify, I think it's obvious, but what is quality control? Quality control are the procedures and practices to ensure that concrete is produced and placed, that the concrete produced and placed meets the required standards and the performance criteria. Well, this covers testing of materials, mix control, and testing of fresh concrete, hardened concrete, and particularly today we are going to speak mainly of these two parts. Well, in my opinion, quality control should be measurable. This means that if we can quantify something and it's possible and reasonable, we do it. It's better quantification than qualification. It needs to be reproducible. This means that we should follow a norm or a procedure. I like to say that our employees involved in quality control, they should know what they are doing. But even if they don't know, the result should be the same. Okay, it's like somehow of a safe procedure and cost effective. This means that it should not be too expensive or too complex. If it's expensive, in the end, the factory takes shortcuts to do it more economic, or the product that you are controlling, in the end, it's not competitive. So we should do something reliable, efficient, but also cost affordable. Well, here I'm showing a table with the quality control procedure for ordinary concrete included in the EN 206. As most of you already know, what is absolutely mandatory is to control the compressive strength. Not even the consistency is totally mandatory. We characterize consistency also. Well, as you see, other properties should be controlled if it is specified by the works or by the client. In the case of UHPC, you know that UHPC is a more expensive material and much more technological somehow. Normally it's self-compacting. In almost all the cases, it has a significant amount of fibers. So all the codes, and here I am showing only what is included in the French norm, because I think the French norm is somehow the most known. But if we go to the Swiss, the SIA 2052, or if we go to the Austin Gate line, or to the American or to the Canadian, more or less it's a similar panorama, but it's mandatory to control many other parameters, both in fresh state and hardened state. If we go to the French norm, you see here you have 3 columns. These are like 3 stages that go from laboratory to the real product. The first one is the qualification of the mix. This means when we are designing a mix, when we are developing a mix, and we have it ready in laboratory or in a controlled environment, then we need to characterize the mix. This is the stage where we characterize, for example, the durability, the density, shrinkage, and this is mandatory following the norm. Here it's mandatory to carry out the flexural tests to obtain indirectly the tensile behavior, the tensile stress-strain response of the material. The second stage is what we call suitability test. This is a scale up. This means if we are going to produce some product, we need to do first, we should do a trial mix in this mixer and in these conditions and filling this kind of element. Somehow it's what the norm calls mock-up, or we can also call as prototype. In this part, we also need to do flexural strength tests on real elements, and this is where we obtain the very famous K, which means the ratio between the flexural strength in the real element and the flexural strength on the prisms of the previous stage. And finally, the control of production is the last column that you see, where it is mandatory to control the compressive strength. And curiously, in this part, it's not mandatory, it's not required to control flexural or even durability, because this is controlled in the previous stage. Well, in the new column that you see in the left side, I am showing what we do in our factory. Well, in our factory, obviously, we produce UHPC every day for different projects. And we have decided, and this is just our approach, because we found out that this is better for us at medium and long term, and that we control continuously also flexural strength, fiber orientation, the density, because the density provides us interesting information or can prevent or deduce what will be the compressive strength somehow. And we also control durability. Every 6 months, we do durability tests to understand how is our mix. And well, first I am going to, here we are going to cover mainly fresh state and hardened state. The first I am going to speak about is how we control flowability. Following the French norm, we need to control the flowability of all of our batches. And we also do this. We use the mini slump test. I think it's quite common in UHPC, because the slump, the typical slump flow test consumes too much material, and it's more tricky, it's more complex. Here I am showing the quality, the mini slump test cone that we do for every batch. You see the area is not very clean. This is because we do it every day. If one day we do 8 batches, we do 8 mini slumps, and we control, we measure the diameter of the fiber. What I can tell you from this test is that it's very practical, because it's fast to do it. You just need 1 employee. For the slump flow, it's a little bit more difficult to manage with 1 person. And it's not only quantitative, because you measure, but you can also observe if there are balls of fibers or any other qualitative criteria that can show potential segregation. What is the limitation of this test? Well, I advise, in my case, our experience is not to do it for fibers longer than 25 millimeters, because the cone has only a top diameter of 70 millimeters, and it's already difficult to introduce the material. This case provides flowability more than viscosity. This is the result of the batches, of the diameter of the batches that we have controlled in the last months. As you see, they are always between 18, 19 and 27 millimeters. Below 18, the filling of the elements is too slow. This decreases the competitiveness, the productivity ratio in the company. And also you may have problems of entrapped air, because it's not as self-compacting as it should be. For higher diameters of the slump, over 27, there is already a certain risk of fiber segregation. So we try to be within this limit. Well, now I'm going to speak about the homogeneity or segregation. Following the French norm, this is optional, or it should be checked qualitatively. In our case, we found a way to determine this homogeneity or distribution of fibers quantitatively. What we obtain is what we call the segregation index, which is, we obtain the volume of fibers in a cube extracted in the last 5% of concrete poured. So when we finish the batch, we fill a bucket, we start filling the element, and more or less with the last 5%, we fill a cube. And we check what percentage of steel fibers has this cube. And we divide by the theoretical content of fibers, the average content of fibers of the mix, because we added them, so we know this value. This is something that we don't do for every batch, obviously. We do it when we develop a new mix or when we have certain doubts or when the environment conditions change. We can do this just to check if our mix is segregating. This is to do so, we use a device that estimates the fiber content of the element based on the inductance measurement. This is very fast, it's accurate. We can do it for fresh state and hardened state. And well, the limitation is that you need this device, but it's already on the market and it has the CE branding. I am going to show a video of how we do this. This video is accelerated, it's multiplied by 2, but in the end, the test takes 2 minutes or 3 minutes. We fill with fresh concrete a cube, which has internal dimensions of 100, 100, 100. We close it because we need that the material doesn't move, and introducing it in this device, which is connected to a mobile phone, it will tell us the inductance in each of the 3 directions. So in the end, it will provide the sum of the inductances of the fibers in each direction. As there is no air inside, the fibers don't change their position, and the value that we obtain after these 3 measurements estimates as the fiber content of the mix. In our case, as you will see now in the left, this batch has 1.06% of fibers. The amount of fibers that we added to the batch on average was 1.09. So this was the last concrete that we are pouring, and the amount of fibers has decreased less than 3%. This means that we are not having segregation. If we want to do this test in hardened state, it's even simpler. Simply we fill cubes, and the next day we can estimate, we can obtain the same value. This is an example of an element which was too fluid or was more fluid than what we generally want, and the result is 1.3, while the fiber content of the whole batch was 1.43. So segregation index is 0.91. So the last concrete that we were pouring had 9% less fibers than what it should have. Okay, this is already in the limit. So it helps us to understand what is the good flowability that we need to have to control a good dispersion and homogeneity of the fiber content. Here you can see a plot of this segregation index related also with the fiber diameter. In general, we can assume that the higher the fiber diameter, the easier is the segregation of the fiber in the concrete. But as you see, the average value is almost 1. This means that the device that we use to measure works good, because on average, the content of fibers is the same than what we add to the batch. And the average deviation when we measure is 4.3. However, only the variability of the fiber doser is 2%. This means that in general, we don't differ more than 2-3% the fiber content than what we really wanted. Okay, this is the way that we use to efficiently control and quantify the homogeneity of our fiber distribution in our mixes. Well, now I go to the hardened state of control of UHPC. We control using prisms of 100 millimeters. The advantage compared to cylinders is that we don't need capping or grinding because the sides are already flat. The French norm suggests that we need to produce 3 cubes at least every 10 cubic meters, or if we have less than 10 cubic meters, we need to do 3 samples. We do 3 samples every day. Normally, rarely we produce more than 10 cubic meters per day, but we produce 3 samples for day and type of concrete. If we modify the fiber content or we are developing concretes for 2 different projects, we do 6 or 9 or whatever is required. Sometimes we also produce an extra cube because when we need to release the strand of pre-stressed beams or elements, we need to test at 18 hours. Here you can see a figure of the last results in the factory, how the characteristic compressive strength has this variation. You can see the red line and how it is over the 130 megapascals characteristic strength required by the French norm. Well, the flexural strength, despite that it is not necessary to do weekly or monthly a flexural strength control, we do it because for us the performance of the fiber is absolutely relevant in mainly in not reinforced elements, but also in reinforced elements because they control the crack width. And we found out that it's better and more economic for us at long term to control this. So we use the 4-point flexural test without notch. And here you can see a figure of the same concrete from the same batch, the result of 3 prisms with 1.7% of fibers. We obtain, and this is the most relevant value for us, the maximum flexural strength obtained. What do we do with this number and with this flexural test? Obtain the post-cracking tensile strength. And for this, we can do it traditionally with a direct inverse analysis. We can, in some cases, if we need a very detailed solution, we can use some other inverse analysis, like the one approved in the norm UNE 83519, which is what we call the 5-point flexural inverse analysis, which was developed by Juan Ángel López, my mate. But for the daily control, we do something simpler. We simply take the ratios that are provided by the Austrian guideline, or we use a similar process than this. The Austrian guideline suggests that depending on the strain hardening level of your UHPC, there is a very accurate ratio between the post-cracking tensile strength of your concrete and the maximum flexural strength of your concrete. And this ratio is between 0.37 and 0.39. I want to clarify, before what is the post-cracking tensile strength. You can see in the left side that it is the maximum tensile strength of the concrete of the composite because it's given by the fibers. Before this is the maximum tensile strength of the matrix, which sometimes is lower and sometimes is higher than the post-cracking tensile strength. Depending on this, our material has strain softening or strain hardening. Before applying this procedure with this simplified ratio, we made a lot of inverse analysis and we obtained ourselves our ratio. You can see this ratio in this figure. You can see the yellow points are the ratio between the post-cracking tensile strength and the maximum flexural strength for our mixtures. And in blue or in green, I don't know what is this color, you can see what the Austrian guideline proposes. So it's very similar, but it's not exactly the same. For us, we have developed the red line as a procedure, as a simple procedure to obtain, based on the maximum flexural strength, the post-cracking tensile ratio of the concrete. So we have our own procedure, but it's similar than the one proposed by the Austrian guideline, which is also, I think it's a very useful tool for a designer. Okay, what do we do with the post-cracking tensile strength? With this value, we obtain the bonding strength, tau. The bonding strength is how much the steel fiber bonds to the concrete. This is what we consider the constitutive parameter for the mix. In the corner below in the left, you can see a document published where you can find much more information about this mesomechanical model. But it was developed by Avi Schraff, which I have seen is now in the audience. So thank you, because your procedure has been very useful. This procedure shows that the post-cracking tensile strength is the fiber efficiency factor lambda multiplied per this bonding strength. And here we have the post-cracking tensile strength because we obtain it from the quality control. We don't know the bonding strength, but we can obtain the fiber efficiency factor. Fiber efficiency factor means how much amount of fiber I have, or how much performance of fiber I have. And this depends on three things. One is the slenderness of the fiber. The higher the slenderness, the higher the efficiency, and we can measure the slenderness. I recommend you to measure the slenderness of your fiber. Don't take what is simply written in the label. Measure the slenderness of your fiber. The second is the volume of fibers that you have. And in this case, until now, we knew the volume of fibers that we have in the batch, but now with the device that I already shown you, we can determine the volume of fibers that we really have in the element that we tested, so we can be much more accurate. And third, the fiber orientation. The fiber orientation can be also estimated with the device I already shown, and I am going to show how. So we can obtain all this, the fiber efficiency factor for the element we are testing. How? We extract a cube of 100, 100, 100, and we introduce it in the device to determine this volume of fibers and also the fiber orientation, because the fiber orientation in the direction of the stresses. We can determine this fiber orientation because we know that there is a clear correlation between the inductances in each of the three axes and the fiber orientation on each of these axes. So we can estimate, based on the result, what is the average fiber orientation in each of these axes. What I am explaining is the left figure. We know this X value. We go to this equation, which is provided by the reference that you see below, and we can estimate the fiber orientation. If we, after doing this with our device in less than 30 seconds, we can plot. I can plot you here the result for different samples tested, and you can see that the fiber orientation is between 0.55 and 0.8, which is logic because our element is between 2 and 1 dimensions. It's something that makes sense. And now that we obtain in the quality control, we know already the post-cracking tensile strength, and we know the fiber amount that we have, we can obtain the bonding strength tau, this constitutive parameter to design, which generally ranges for UHPC mixes between 9 and 13, depending on the fiber content, depending on the cement content, on the capacity on the mix, and so on. But it does not depend on the fiber content or the fiber orientation. This is the key. When we know this bonding strength, we can predict for any element where we know the fiber amount, we can predict the post-cracking strength. This is a plot of some of a population, a group of a sample of beams with the same material, how there is a clear correlation between the post-cracking strength and the fiber efficiency factor. And this slope is the bonding strength, in this case, 12 megapascals. So now comes the question, is this better to design and to obtain the bonding strength than working with directly with the post-cracking tensile strength? Here I am showing the result of 36 samples of concrete, 1.2% of fibers, concrete used for the same project. You can see that the variability of the compressive strength is 4.9%. For the tensile strength, FTU, or for the flexural strength, it is 16%. Why? Because in the samples of the quality control, the fiber orientation is different. And sometimes the fiber content also, logically, is different because there is some statistical variation. However, after doing the procedure, the variability of the bonding strength tau is only 5.4%. So it is almost as constant as the compressive strength, because in the end it's intrinsic, is associated to the matrix and to the type of steel that we use in the fiber. So as we can determine the fiber amount that we have in the beam, we can avoid this variability. So now comes the question, when we design, okay, we have the bonding strength of our concrete, of our UHPC. How can I know the lambda, the fiber efficiency factor to design an element? Well, we choose the slenderness of our fibers, so we know the slenderness. Okay, we can decide how much fibers we add to our concrete. And we can even reduce this if we know that there is a lot of variability later in the distribution. But we can know this. And here is the main question. Can we estimate the fiber orientation factor in an element? Well, we can do it in different ways. The first, and this is the most complex, is based on experience. We cut sections, and through image analysis, we determine the fiber orientation. This is expensive, and it's complex. We have done it sometimes, but it requires to waste an element. The second is use the fiber orientation factors provided already by some guidelines. Here I am showing only some of the fiber orientation factors provided by the Austrian guideline published two years ago. So they suggest in each of the directions, depending on the thickness of the element, what the factor orientation, what fiber coefficient you can use. There are many other types of elements. I am only here showing two because I don't have space, but this is a very useful tool for a designer. And the third is with non-destructive tools. So there are non-destructive tools similar to the based also on inductance that can be used to estimate fiber orientation and fiber content in elements that are thinner than 7 centimeters and without steel reinforcement. In case that we want to understand how steel reinforcement is going to affect to our fiber orientation, we can replace the steel reinforcement by glass fiber reinforced polymers or any other kind of rebar which is not metallic. And then we will see how is the fiber blocking, how is the fiber oriented around the reinforcement, but not affecting this device. Here you see a slab, the results of doing this determination in a slab of 2.7 per 2 meters. And you can see in the left side how accurate can be the determination of the fiber content, which here varies between 1.8% and 2.4%. So fibers are not distributed perfectly. We also see the fiber orientation coefficient in the vertical direction, and it makes a lot of sense because next to the sides is approximately 0.7 because there is some wall effect, and in the central part it is lower. And even in the right side, in the right side, you can see the principal directions of the fiber orientation. This can be done. It takes a lot of work, but sometimes it's very useful because depending on how we feel an element, these values are going to change. And now with technology, we can know this. And with this formulation, this mesomechanical model, we can predict what will be the post-cracking strength. And here the main issue is if we measure in one mock-up or in one prototype, we know the fiber orientation, but the question is how much this fiber orientation coefficient changes when we produce 10 units or 20 units. So the key is what is the variability of the fiber orientation factor. And it's something that we can do measuring repetitively in several elements and learning through experience in panels or in walls or in beams how much this fiber orientation coefficient changes. So to summarize, well, UHPC requires obviously more quality control than testing ordinary concrete. The latest norms and guidelines and also the latest technologies in non-destructive testing help to implement it efficiently. Even if it's not mandatory, doing more quality control, intensifying the quality control can often reduce the costs, enabling to detect early the deviations. So it's easier for us to understand what has happened in the concrete. And I would say also that a precast UHPC factory with a wide and powerful quality control is somehow an industrial scale lab where we can, which can boost a lot the continuous improvement and innovation, thanks to the amount of data that you can generate in a factory. And that's it from my side. If you have any doubt, we can speak about it.
Thank you very much, Esteban. So before asking you a couple of questions, one question for you and another for Bent, some useful information for the attendees. So we actually have recorded this workshop. So the recording will be found on the website, on Natursea-PV website, and on the YouTube channel of Natursea-PV project. So you can also follow our social media. Natursea-PV is on X and on LinkedIn. So if you look for it, you will also see the recording published there. Concerning instead the questions, there was a question for Bent, a previous question that was, I want to ask if these bridges are, no, sorry, probably was for Vu. I want to ask if these bridges are competitive considering the savings in maintenance, or they are competitive from day zero due to the savings in transport and commissioning. Dr. Vu.
Oh, sorry, I didn't catch you. What was the question again?
I can read it again. So, someone asked if these bridges are competitive considering the savings in maintenance, or they are competitive from day zero due to the savings in transport and commissioning.
All right. You see, generally, in most part of the world, if your project do not have immediate cost saving, basically it's nothing much to talk about. So to answer your question is our UHPC alternative or our UHPC product system, they are actually either same price as the conventional or have saving. But the savings very much depends on the locations or the nature of the project. It can be as low as maybe 5 to 10% to as high as to 30 to 40%. It depends on the location. Yeah.
All right, thank you very much. So there's a question instead for Esteban. The question is, which is the Portland cement that you are using actually? Portland cement class 52.5R or plus silica fume fly ash GGBS?
This is confidential.
All right. So
we use a variety. We use a variety of cements, but in general, it depends on the project and it depends on the situation.
All right. So thank you very much. So this concludes today's workshop. So I want to thank once again the speakers and also the attendees that stayed with us. You were quite a lot, and we want to thank you very much for being with us. For any question, you can contact us, or we will try to answer to everyone. And keep following us, because there will be more events like this in the near future from Natursea-PV project. So if you want to know about them, just follow us on social media or keep an eye on our website. So I won't take more time, and I want to thank you all once again, all of you. And this concludes today's workshop. Thank you very much. Goodbye.
Bye.
Thank you. Bye.
Thank you.